Hi everybody, this is Yatharth Dubey, and I'm going to be talking about polynomial size branch and bound trees for random multidimensional knapsacks. And this is joint work with Shantanu Day and Marco Molinaro. So first, just to introduce the problem, we consider an M-constraint knapsack problem where all of the data is drawn uniformly from 0, 1, and the right-hand side is a vector of constants between 0.5 times n. Here we consider branch and bound algorithms that select the node with the worst dual bound and employ any variable selection rule. We note that a node is branched on if and only if its LP relaxation has higher objective value than the optimal 0, 1 solution, okay? And our central question is how many such nodes could there be? And the answer is this quantity presented here with high probability, and importantly, we note that this is actually polynomial in n. So I actually want to start by noting that all of the pictures are for a single constraint knapsack so that it can be shown in 2 dimensions, but all of the results are written and applied to an M constraint knapsack, okay? And so this is kind of a picture of the solution space. So each of these blue dots are a 0, 1 solution that's plotted by total weight and total profit. And this green curve, f of b, is actually it plots the optimal LP relaxation value of the problem over right-hand sides, okay? And this pink line b is the right-hand side of our instance, and this orange point here is actually the optimal 0, 1 solution for our instance, all right? So this distance gamma shown here is the additive integrality gap for our instance, okay? And this blue curve, the cyan curve, is just f of b shifted down by gamma, so f of b minus gamma. And so these points here in pink are actually exactly what we call good integer solutions or good 0, 1 solutions. I'll go back and forth between that during the presentation. And these are the points that are above the cyan curve, okay? So the first part of the proof, we just want to show that the number of nodes branched on in any branch and bound tree is at most n choose m times the number of good integer solutions, okay? So here's a zoomed in picture. And now we consider an LP optimal solution that we see during the course of branch and bound that's actually branched on, all right? And it has this one fractional component. And we note that in this picture here, it must be in the convex hull of these 2 0, 1 solutions, okay? And here's another example. So we note 3 things. An LP optimal solution that is branched on must be above the blue curve at this pink line B. And it must also be in the convex hull of some 0, 1 solutions. And therefore, since this region under the blue curve is convex just by LP sensitivity analysis, there must actually be some 0, 1 solution above the blue curve, so a good 0, 1 solution, for each branched on LP optimal solution. So in a sense, this says that by counting the good 0, 1 solutions, we don't miss any LP optimal solutions that could be branched on, right? But when we count these good 0, 1 solutions, each good 0, 1 solution could correspond to several LP optimal solutions that are branched on. So now our question becomes, for each good 0, 1 solution, how many nodes can be branched on in any branch and bound tree? So let's focus on this particular good 0, 1 solution. And note that this good 0, 1 solution can correspond to n LP optimal solutions that are fractional and branched on during the course of branch and bound, all right? That's in this case because for a single constraint knapsack, there can be at most 1 fractional variable in an LP optimal solution. But for an M constraint knapsack, there could be up to m fractional variables in an LP optimal solution. And so the number of possible sets of fractional variables in an optimal LP solution that can round to a single good 0, 1 solution is at most n choose m, all right? And so now it remains to show that 2 different nodes in a branch and bound tree whose LP optimal solutions can round to the same 0, 1 solution cannot have the same set of fractional variables, okay? And the proof of this statement is pretty simple. So first, consider 2 nodes in a branch and bound tree that aren't descendants of one another. All right, so in this case, N1 and N2. And so look at their most recent common ancestor, so that's N0, and the variable that's branched on at N0, which is xj, right? So N1 has xj equals 0, and N2 has xj equals 1. And in fact, this means that they cannot round to the same 0, 1 solution. So it actually, for them to round to the same 0, 1 solution, they must be descendants of one another, all right? So now consider two nodes that are descendants of one another, so N0 and N1. Now note that xj, the variable that's branched on at N0, was fractional in the LP optimal solution at N0. But since it was branched on at N0, for all of its descendants, it's no longer fractional. And so therefore, they cannot have the same set of fractional variables. All right? So by now, hopefully, you all believe that the number of nodes branched on in any branch and bound tree is in fact at most n choose m times the number of good 0, 1 solutions. And so all that's left to show is the second part of the proof. We just need to count the number of good 0, 1 solutions. All right? And we start by actually partitioning the solution space as shown here. And in fact, when we partition this way, there can be at most n choose m such regions. All right? And so what we're going to do is we're going to count the number of good 0, 1 solutions in any one particular region. Now, just quickly, this picture on the right side here is actually each of the variables or items plotted by their weight and their profit. So the key observation here is that for any good 0, 1 solution z, its vertical distance from this curve f of b is actually exactly the sum of the absolute reduced costs of all of the 0, 1 variables that are different in z than the LP optimal solution that achieves this value f of b above z. So just to go through a few examples. So on the left side, this green good 0, 1 solution corresponds to when we change the value of these two 0, 1 variables that are highlighted green on the right side in the LP optimal solution that achieves this value f of b above this green 0, 1 good solution. Here's another example. Okay, so this 0, 1 solution corresponds to when we change these two items highlighted in green on the right side. And a third example. Okay, and so if in fact the integrality gap is small as shown here, and that each of these slabs that we show on the right side, I'm going to skip the details for now, but if each of these slabs have about their expected number of points, then in fact we can say that the number of possible sets of variables that can be different and still be within the integrality gap away from f of b is at most m to the 4 times n to the 4. All right, and this exactly counts the number of good 0, 1 solutions in this region. And so this first assumption actually occurs with high probability due to a result of Dyer and Fries from 1989. And the second assumption is something that we prove in our paper, and I'm going to skip here, but I'd be happy to talk about offline. All right. So now wrapping up, here's kind of the picture, right, of the solution space partitioned into regions. And we look at any one good 0, 1 solution, and we note that it can correspond to at most n choose m LP optimal solutions that are branched on during the course of branch and bound. And that there are at most m to the 4 times n to the 4 good 0, 1 solutions in a particular region. And that there are at most n choose m of these regions. All right? And this gives us our desired quantity. All right, thank you everyone for your attention, and thank you to the organizers for the consideration. Thanks.